Hello, everyone, and thank you for attending our session today. My name is Xavier, and this is my friend Antonia. We both work at Giant Swarm. I work as a solutions architect, and Antonia is a platform engineer. And today we are going to talk. Oh, that goes pretty fast. Today we're going to talk about Frankenstein's cluster. So we'll see in a bit what it means, but in terms of what we're going to talk about, we're going to start with the few prerequisites about cluster and node lifecycle using cluster API. Then we'll talk about the use case around hybrid clusters and what brings us here today to give a talk. We'll mention that Frankenstein cluster that was in the photo, and then we'll finish with a note on hosted control planes. And let's start with cluster API then.
Right. So as mentioned, we work at Giant Swarm, and Giant Swarm offers a managed Kubernetes product. And basically, we manage Kubernetes clusters using this thing called Cluster API. So in order for things to make sense, I'm just going to explain how it works first. So cluster, this does actually jump pretty quick. So cluster API is a Kubernetes subproject. It's from the SIG lifecycle, and it's basically Kubernetes native way of managing Kubernetes clusters. So your Kubernetes clusters are going to be represented through custom resources. Those custom resources get reconciled. And then the thing that makes this very interesting for companies like the ones that we work for is the provider model. So you can plug in any sort of infrastructure provider that you may want to run on, like AWS, vSphere, Azure, or even like bare metal providers and so on. The central concept of Cluster API is the management cluster. So this is where your CAPI controllers and your custom resources live. And from there, you reconcile several workload clusters. These workload clusters and management clusters can be on different providers. You do need networking between the management cluster and the workload clusters, though. So in case of our customers, what we do is we provide them with a management cluster or several management clusters, and then they can just create their workload clusters as they see fit, basically, to manage their workloads. Any cluster API cluster kind of looks like this. So there's the central resource, which is the cluster resource, and then you get a control plane, you get machine deployment or machine pool, which represents your workers. And then there's one machine CR for each node in your cluster. Then there is the infrastructure layer, which you can see here in yellow. So this is a provider-specific resource that pairs with the provider-agnostic ones. And in this case, there's like the example vSphere. So in case of vSphere, you get a vSphere cluster, vSphere machine, and so on. And this infra layer is the one that talks to your actual cloud provider or your hypervisor API. Again. Then there's the bootstrap layer here, which this contains your cloud init or ignition data, which turns any fresh VM into an actual Kubernetes node. We use kubeadm. There are other providers as well. So basically the ignition data comes from a template, and this template lives inside something like kubeadm control plane and bootstrap, like a kubeadm config template, which is called bootstrap config template here, because as I said, can be different provider as well. And then all of these resources have a relationship to each other. So this looks a bit messy. Basically, what happens here is that the cluster has an infrastructure reference to the infra cluster, and then a control plane reference to the control plane. And the machine deployment references both the infra template and the bootstrap template. And then there's also an owner reference, which basically always goes from the lower resources to the ones above, so that basically it is known where they belong to, right? And so CAPI always knows which resources belong where. And this is a bit of kind of a convoluted slide. And the reason that I'm showing you this is not that you remember this, but just to know that this is going to get a bit messy later, basically. Then you do have controllers reconciling all of these resources. The green one you see here is the core CAPI controller. That one reconciles the cluster and machine deployment and so on. And then the infrastructure provider controller will talk to hypervisor API or like cloud API and reconciles the infra layer. And then you also get like control plane controller and bootstrap controller, which will work with something like kubeadm to take care of your cloud init or ignition data, basically, so that each machine can join your cluster. And then there is this other element which runs on the workload cluster, which I think you are going to talk about.
Yeah, so this is another component that goes along with cluster API usually. So when you run on a cloud or hypervisor provider, most likely you're going to want to run a CCM, so Cloud Controller Manager. So this thing runs inside the workload cluster, so not in DMC, and it's a bridge between the Kubernetes and the underlying infra layers. So what it means, it has 3 different controllers. So there's the node controller that will initialize the new node and remove the or remove them from the cluster and infra provider. There's a root controller that will set up the routes for inter-node communications if applicable in the infra provider. So for instance, in vSphere, it's not applicable because it's just a dumb hypervisor, but in AWS Azure, you have a whole lot of stuff going on. And service controller, same thing, it can create load balancers, but like providers like vSphere don't have such thing. So this is pretty important for the node lifecycle. So at first, when a machine CR is created, it starts in the pending states, and then the core CAPI controller waits for sets the owner ref and waits. Then the provisioning states. So here three things happen. The bootstrap controller will generate the cloud init or ignition data, depending on whether you use like an Ubuntu-based OS or Flatcar, for instance. The infra provider spins up the VM and will inject that metadata using the infra-specific system of metadata passing, and then the CAPI will wait for both to be ready. Now, when the VM is up, the infra provider will set the provider ID and mark the machine as provisioned. So at this point, the VM boots up, kubelet starts, kubeadm starts, and it will initialize the cluster or join it if it is a worker node. The node registers itself in Kubernetes, as we can see here, but it currently has an uninitialized taint, meaning we can't schedule anything on that node. So the CCM will detect the new node. It will query the provider API to see that, yes, there is a corresponding VM. It matches the node. It will set the provider ID, labels, and remove that taint. That way, now the node is actually ready and running, and we can use it to provision workloads. So now that we have this out of the way, let's transition to a hybrid setup and the use case that we are going to talk about today. Sometime last year, this customer from Shutterstock came to us, and they wanted to escape their VMware license cost increase. As you might have heard, Broadcom acquired, then prices jacked up, etc. Yeah, you know the drill. So their idea was to move to bare metal because they want to save on hypervisor costs, licenses, overhead, etc. But the physical servers are pretty large, like lots of CPU, lots of memory, and dedicating 3 of these to control plane nodes would be a bit wasteful, so they did not want to do that. So they were like, why don't we run the control planes in virtual machines instead? And sure, why not? We also thought that we could remove the control plane taints that prevent workloads from being scheduled, but this is not like best practice, so we did not want to do that for our customers. So the plan was pretty simple, having to, like the vSphere cloud the CAPI provider, we installed the Metal Cube CAPI provider, which is like a bare metal infra provider. We have our vSphere cluster, we add the Metal Cube node pool. It works, easy. So we thought. We already had some experience with hybrid management clusters, but by that, I mean an MC running in the clouds and then worker clusters running on-premise. So some of our customers, for instance, they run an MC in AWS or Azure. Then we have an IPsec tunnel between the VPC and the on-prem subnet. And from there, because we have connectivity, we can deploy workloads and manage the lifecycle, having GitOps and all these things over like a large area, like geographical area. But this is not what we need here. This is just like each cluster will be on the same infra provider. So what we want to do is having a VC with control planes running at virtual machines and workers bare metal. So essentially control planes and workers on different infra providers. How hard could it be, you might wonder?
Well, as it turns out, it jumps twice. So this is a vSphere cluster. So this is a standard issue CAPI cluster. There's one infra provider here, and it is vSphere. And this cluster is alive, and it is running very healthily. And now our idea was to add a node pool in another provider to this, just to test it out. So we didn't want to go and commit to something like a bare metal provider, like Metal Cube. And instead, we just wanted to try if we can even just have a node pool in a different provider, right? So we decided to use vSphere and Proxmox because we can run these two in the same environment, so we don't have to worry about any networking stuff, and just added this node pool. As you can see, there's also now two infra cluster objects. There's a Proxmox cluster object as well. And before you ask, we actually looked into this upstream before doing it, and we very quickly found out that it is not really a supported use case. So there's no documentation on how to do this on the cluster API side. People in the community tend to say, don't do this. And also when we check the code, we noticed that it's just not expected that there will be another provider. It's just always assumed that there's one. So we knew that there were going to be some dragons, but no surprises. We tried this anyway, right? So we created a monsters, and this is what it looked like. So we had the second infra provider, Proxmox, and then everything at the bottom is pretty much the same. So the node pool has infra template, it has bootstrap config, the machines have all their references, and this is pretty much exactly the same between vSphere and Proxmox. But when you look at the top, we get into the issue because we have two infrastructure cluster objects, and one for vSphere and one for Proxmox, but there is actually only one infrastructure reference. So this is a problem. And we did make this work, but it's a bit of a trade-off. So the cluster kept the infrastructure reference to the vSphere cluster, and the Proxmox cluster only has an owner reference to the cluster. So this means that the Proxmox cluster knows that it belongs to this cluster, but the cluster doesn't know that it has this part. And cluster CTL, which is the cluster API CLI tool, also wouldn't find this part. And so CAPI will reconcile these resources, obviously, but it kind of sees half a cluster, and we were smuggling the second infra provider in through the back door, essentially. One thing worth noting, I'm going to show this to you in a sec, but one thing worth noting is that we added this external managed control plane true in the Proxmox cluster resource, and all it does basically is it prevents Proxmox from trying to manage the control plane so that there is no problems with vSphere, basically. And can you give me the demo? All right. So we recorded this, and I think it's also a little bit sped up, and I'm going to try to do my best to speak over it. So we have our management cluster here. So you can see this vSphere cluster that I showed you earlier with all the resources. And then there is the, did you stop it?
Yeah, actually, hang on. Do we have the, is it the right?
I think this is right. You just have to let it play because I have to talk. Okay, and this is the workload cluster. So we have our nodes here. And then what we're going to do is, this is actually the wrong demo. This is the one that has the fix. Can you give me the other one?
Oh, is it the wrong one?
Yes, it is.
Sorry.
We've been doing this for the first time, and it's a little bit difficult to do the demo like this on the other screen. So very sorry about that. I need this one. Okay, again, pretend that didn't happen. So here is our management cluster with the vSphere cluster that I showed you earlier. And you can see that we have some nodes. It all looks good. Now we're going to apply the Proxmox. Okay, this is not how that works. Proxmox resources. And we will basically wait for these Proxmox machines to create some Proxmox nodes, hopefully, in our workload cluster at the bottom. And here they are, and now they disappeared. And the question is why? And these logs here are the logs of the CMC, which you saw earlier. And those might help explain what went wrong. So I'm just gonna, I don't know.
Yeah.
Okay. I'm just gonna show it to you here because I'm not sure it was that visible in the demo. I'm sorry. But this was the log that came up from the CMC when basically the nodes appeared and then disappeared. And basically what it says is that it has an error discovering this node. And we can see the ID of this node has a Proxmox prefix, but this log is from the vSphere CCM. So the vSphere CCM is looking for this node, which doesn't exist in vSphere, obviously, because it's not a vSphere node, right? But vSphere is all that this thing knows. And so what it does is it just deletes the node because it cannot find the VM, right? And you may have seen this one coming if you paid attention to the life cycle slides that Xavier showed earlier, but we actually didn't see it coming, so we did not pay attention. So what happens is basically that our node transitions from running to VM deleted because the CCM cannot find the VM, so it thinks it must have been deleted, and then to node deleted because the CCM is deleting the node. And then it goes back to pending because the machine deployment will always create a replacement. And then it gets deleted again and so on. And this is basically just this kind of endless cycle where the vSphere CCM keeps removing the Proxmox node because it does not exist in vSphere. Kubernetes is not designed to run multiple CCMs in one cluster. And you might say if we were using bare metal, we might not have two CCMs. However, in this case, the vSphere CCM would still try to remove the node which it cannot find. So that might not even help. However, we were thinking that aren't these provider IDs very obviously different from each other? So they have a prefix that literally sets the provider in them. So what we decided to do was we just patched the vSphere CCM to check for the prefix. And then if that prefix is not vSphere, it should just leave that thing alone, right? Just leave the node alone. Back to the demo, which is probably not going to be that easy to see again, but let's just do it. So what we have right now should still be the same cluster. Yeah, we still have a Proxmox node pool here. And then we probably still don't have our Proxmox node though, because it got deleted, right? So now what we're going to do instead is we're going to patch the CCM image on the workload cluster. So we changed it. It should now be this PID test. That's our patch. Now we're gonna watch the nodes and we're gonna remove the machines so that it gets recreated and see what happens. We should this time get some Proxmox nodes running in our cluster. Let's see. And here they are. And as you can see, they don't get deleted anymore because of the patch that we did. And we can also check the CCM logs again. Thanks. Okay, so this is basically the logs. This time they just said skipping the node. So what we did is essentially what I just said. We are not doing anything with this node because it doesn't have a vSphere prefix. So we have broken our cycle, we forked the vSphere CCM, and it now ignores the VMs with a non-vSphere provider ID. That's awesome, right? So it's alive, and you can also get this PR here. We did not submit it upstream because it's very hacky and they probably don't want it. But our one still lives. However, at what cost? So basically now any upgrade that we might get for the CCM or for the CAPI controllers or for the provider controllers who break our cluster potentially, which we wouldn't know because upstream nobody is expecting or supporting our use case. Also, our on-call engineers might go online at night and just see half a cluster and they don't know where the control plane is, and it might be a whole thing. And also we have to now maintain this fork of the CCM and maybe some more forks as well, and we might have to do that indefinitely as well. It's going to be a nightmare to schedule any pods on these different infrastructures, and we don't have any upstream support, cannot use cluster-CTL. So we actually have a Frankenstein cluster in the sense that it is alive, but it's also not production ready, right? It's not a person. So we had to find something else.
Yeah, and this is where hosted control planes are pretty interesting in our case. But first, let's wonder what makes a control plane node a control plane node in the first place. So you have a kube API server, a scheduler, a controller. Control manager. So that's 3 containers. Do we actually need full VMs, full cloud instances just for these 3 containers? It turns out we don't. So hosted control planes is, instead of running specific control plane nodes within the workload cluster, we will run these control plane components as pods somewhere else. So in the case of cluster API, it's most likely going to be in the management cluster. So the benefits are pretty obvious here. Significant savings on node overhead. So you don't have an OS to run with all the pods that go along with it on the control plane nodes. No node bootstrapping. So the provisioning is much faster. You can get control planes in a few seconds. Same for like rolling updates and this kind of stuff. And the multi-tenancy aspect in the case in that you can run many control plane environments within the same management cluster. So you can pretty much consolidate your resources. Now, there are a few players at the moment. There's Mirantis with Cosmotron, Red Hat Hypershift, vCluster from Loft Labs. Gartner also does some of this stuff in their product. And Kamaji. I'm sure there are others out there that I haven't listed, but I think they are the main ones. So we're focusing on Kamaji here. So it's an open source project maintained by the folks at Clastix in Italy. The good thing for us about Kamaji is that it has a cluster API control plane provider. So we talked about kubeadm before. This is what it's going to replace for the control plane side of things. So we can have multiple work cluster control planes in the same environment, and you can also share the database between control planes. So you can have one etcd cluster, and then many of your clusters will connect to it. Now, it's worth noting that to get access to stable releases to Kamaji, you'll need the enterprise subscription, which comes with other things. But otherwise, by default, it will be pushed automatically. So you'll have to do some testing to make sure everything works fine. Oh, well. So anyway, let's build our Kamaji-based workload cluster. So this is the same diagram we had earlier, except it's a bit different. On the left-hand side, we used to have kubeadm control plane, and now we have Kamaji control plane. So the Kamaji control plane here is reconciled by the control plane provider of Kamaji. This will create a tenant control plane. This thing is reconciled by the Kamaji controller. And this will create a pod deployment, which will trickle down into your control plane pods. Now, note that one pretty handy thing for us at GenSwarm is that your workers still join the cluster with kubeadm, because we have a whole templating thing with Helm charts. So we didn't have to change any of that. So your kubeadm workers will still join the Kamaji-based cluster the same usual way. And we still need some sort of key value store to store the data of our API. There is another CR called the data store, which is also reconciled by the controller. And it will create a stateful set to have the persistence of our database. So you can, I think there's etcd, Postgres, and MySQL by default. And yeah, then it's exposed on a service of type cluster IP, if I remember correctly, and the control plane pod will connect to it. And this is the controller view. Again, pretty convoluted. There's quite a few things going on, but it's not that complex. Like there's just the same thing we saw earlier with the controllers, except now we have 2 extra controllers for the Kamaji stuff. And the fact that we do this is that we can have indeed our control plane nodes, well, control plane components and worker nodes on different infra providers, because the MC could be in vSphere, and the VC, well, the workers might be in Proxmox. Now, we're going to look at what it looks like. So we don't have a cluster to start from here. So we're going to create from scratch. So we're using the Giant Swarm way of deploying a cluster. So everything is bundled as a Helm chart to simplify the process. So we have Helm hooks to automate with jobs to automate complex tasks. We create one etcd cluster per worker cluster, and includes all the bits that we use, like monitoring, security, and all that stuff. So here we will start by creating our resources, and the data store will be the first one to provision, because this is the prerequisite for a control plane. We need to have some sort of database. So we have the data store at the bottom, which populates etcd pods at the top based on a stateful set. Now, once this is ready, the Kamaji controllers will take over, and they will start creating. Now we have a tenant control plane, which will create a pod deployment for our control plane pods. I should stop saying control plane nodes. And they should come up in a second. Now we have more and more pods. So we've set the replicas to 3 because we want 3 control plane pods. And now we have everything running. Now our machine deployment, so the node pool is provisioning 3 workers. So the control plane pods are in the MC in vSphere, and the workers are getting created in Proxmox. We use Proxmox because it's much faster. It's pretty easy to work with. Like bare metal is really, really slow. So we're just like proving it. And here, let's take a look at what the Kamaji control plane pods look like. So there's 3 of them. We have 3 containers in them, so the API server, the scheduler, and the controller manager. And we also have connectivity server, which is a helper tool that facilitates networking between our control plane components and our worker nodes for stuff like join the cluster, webhooks, and everything. And now I'm getting the kube config from that cluster, taking a look at the nodes. Yeah. And now we have a working cluster. Now we had to tweak a few knobs. So we had to disable the components that run on the control plane. We had to rework some stuff for etcd to work, network policies for webhooks, connectivity, and the fact that data store CRs are non-namespace, they are cluster scoped. We had to play around with our back to make it work in our environment. Few trade-offs in this is not specific to Kamaji, it's mostly like hosted control planes. Your management cluster becomes a single point of failure, so you have all your control plane components running there. So if the thing burns, then like everything, all your control planes burn. The risk of noisy neighbors appears here because you will you consolidate all your resources in the same place, so you have to be very strict with resource reservation. Again, with RBAC, like I mentioned, if you have many tenants, many customers, you need to be careful with that. And database multi-tenancy, yeah, you can share database between clusters, but should you? So it is a pretty good tech. At the moment, it is supported. It works very well. I think it makes sense to save resources, and I think it's well maintained as well. But it does still raise the question, should we be able to mix infra providers in the same CAPI cluster? I think it's kind of up for debate. But this is